A novel exponential pulse decay modulation multiplier for VLSI neural. This paper introduces a new Epdm multiplier circuit based on the dynamic charge of most differential configuration resistor. In addition, shows that the actual response of a conventional Epdm multiplier is not linear and pseudo-linear resistor realization is VDS and VTN dependent. This active resistor has matched devices biased in the triode region and enables the multiplier to enhance the output linearity. The proposed technique removes the influences of bulk source and drain source voltages on circuit resistance by taking into account the effects of channel length modulation, making the developed new multiplier suitable enough for the architecture's implementation of several analog VLSI neural networks. Index terms: artificial neural network, synapse circuit design and exponential pulse decay modulation technique. Introduction. The application of artificial neural networks, in analog chip designing resulted in the solutions to problems of geometry, propagation delay, parametric nonlinearities, and power consumption which were once considered difficult. 2 and 7 have shown that, due to its power consumption and critical matching, designing of an analog multiplier is among the challenges of analog circuit design. The multiplier finds its applications in communication circuits, including filters, modulators and mixers, and can be implemented using both BJT and MOS technologies 14, 15, and 16. Since BJT consumes more power, the MOS multiplier with active load resistor becomes strong candidate for end usage for low power design. Under the conditions of negligible channel length modulation and mobility reduction, 3, 6 and 11 have shown linear response of an Epdm multiplier when compared to conventional analog techniques in terms of low power and area requirements. An Epdm multiplier independent of VDS and VTH changes is proposed. The paper is divided into following sections. Section 2 and 3 present the basic operation and design of a conventional and modified Epdm multiplier with double MOS configuration, respectively. Section 4 presents the analysis and results of SPICE simulation of both types of Epdm multipliers. Section V elaborates on the comparison of both Epdm circuits followed by the conclusion. 2.2. The conventional Epdm circuit. The conventional Epdm circuit, as shown in Figure 1, modulates the input by a weight signal through the decay time of a single-sided exponential current pulse. The delivered charge packet Q can be obtained using equation 1. 1 dash dot equals dot dt, t, u eqt. Where are the step function and is the charge delivered? And are constant values controlled by the input and weight signals respectively. The neuron input signal with its weight simultaneously enables two-quadrant multiplication complementary arrangements to charge packet of the distribution bus. 2. To eliminate the influences of VDS and VTN upon the AC resistor realization, a modification in the conventional Epdm circuit is made. The principle employed here is to use 4 identical devices biased so that the influences of VDS and VTN variations are cancelled out. This design uses a double MOS differential configuration resistor, as shown in Figure 2. The characteristics of the AC resistance can be obtained by assuming all of the devices are matched and operate in the ohmic region. I1 and I2 are obtained as follows. Advantage of the new Epdm multiplier. The modified Epdm circuit has added advantages when compared to the conventional circuit. Because there is no static path between bias voltages, it will result in low power consumption when integrated at VLSI levels. It successfully reduced the influences of VDS and VBS by using the double MOS differential configuration with matched devices operating in the ohmic region, as indicated in Figure 6. The modified circuit not only makes the AC resistor linear, but removes the influence of the bulk source voltage. The effect of the channel length modulation has been reduced as all devices are operating at the ohmic region. And, since .VDS is so small in this region, it has little effect on ID due to neglect of the channel length modulation and body effects. The output becomes more linear and the THD problem is ignored forever. The die area is small compared to the previous design because the smaller transistor dimensions can be chosen than those in the other circuit. Although the linearity of the new circuit is very good over a wide range of input signals, the dependence of output charge on prevents the circuit from being an ideal linear multiplier. The combined transconductance, GM, of devices N1 N4, or P1 P4, must be small enough to ensure a high 2SV. Equivalent resistance between node B and VDD, or node A and plus VDD, to assure good capacitive coupling from to node B, or to node A. It may happen to see an offset in the output due to non-ideal matching between devices in the aspect ratios, parasitic capacitances, and threshold voltages. \SV. Proposed Epdm and synapse circuit. The suggested Epdm multiplier circuit shown at Figure 7 became the more suitable synapse circuit for building the new synapse memory matching cell. The proposed circuit is basically an enhancement Epdm with 2 or more gates. One of the gates is left floating and other select gates act as the gate of a regular enhancement MOSFET. Referring to figure 8 and the total current described by equation 22, that controls the on and off states of biological neurons transistors by calculates the weighted sum of all input signals. Analysis of the proposed synapse memory cell. The proposed circuit has been utilized to produce the sum operation with no DC current flows. As a result, a DC current-free operation of the cell has been established, making it possible to build a low-power system. The circuit is very simple in concept and construction. It consumes a small chip area because there are no switches, as in most classical matching cells. The proposed synaptic memory cell design with floating gate potential and real-time monitored during data writing achieves accuracy and high speed for analog voltage storage through the thresholding action of proposed inverter. Because no complicated control circuitry is required for weight updating, the new version cell allows high-density integration of a synapse cell as well as a high-speed learning operation of a proposed self-learning neural network. The static power dissipation in each inverter is zero in both of its states, where the dissipation due to the leakage currents is so small as to be negligible. A low resistance path exists between the output terminal and ground or VDD. These low resistance paths ensure the output voltage is independent of the exact values of W/L ratios or any other device parameters. Furthermore, the low output resistance makes the inverter less sensitive to the effects of noise and other disturbances. Conclusion. The proposed multiplier can modulate an input signal based on a locally stored weight voltage. The modified Epdm multiplier circuit can produce efficient computations in the analog domain with a reduction in power and area requirements. Although the linearity of the new circuit is very good over a wide range of input signals, the dependence of output charge on prevents the circuit from being an ideal linear multiplier. The average actual power consumption of the new circuit will be less when compared to a conventional Epdm circuit. The combined transconductance, GM, of devices N1 N4, or P1 P4, must be small enough to ensure a high equivalent resistance between node B and VDD, or node A and plus VDD, to assure good capacitive cooling from to node B, or to node A. There is a possibility of appearance of an offset in the output due to less than ideal matching between devices in the aspect ratios, parasitic capacitances, and threshold voltages. Practically, I observe that the output of the proposed matching cell is not exactly zero. This is due to the non-perfect matched device parameters and the parasitic capacitance coupled to the floating gate. The speed of operation of a digital system as a computer is determined by the propagation delay of the logic gates used to construct the system. To obtain lower propagation delay and faster operation, a higher process transconductance parameter should be utilized and the transistor W/L ratio increased. There are design trade-offs because these conditions increase the dynamic power dissipation.